Alright, so we've worked through the first two sections of Chapter 5. And let's do a quick review. Section 1 and Section 2 introduced the circumcenter and the incenter. These are two types of triangle centers. And if we can remember a little something about the circumcenter, it is the center point for a circumscribed circle. So we get these equal radius measures. The incenter is the center point for the inscribed circle, where we get equal distances to the triangle sides. Alright, let's hide these, incenter and circumcenter, and let's meet our new triangle center, the centroid. The centroid is the intersection of medians. And our definition of a median is it's the segment that connects a vertex to the opposite midpoint. So if I were going to mark with congruence marks, this is what we would have if I constructed all three medians and found the intersection of those, which is a new triangle center called the centroid. The proof we'll be completing in this video is the centroid theorem, which is on page 314 of chapter 5. And what we're given is a triangle with midpoints of two sides and then two medians constructed. And we want to prove that the centroid divides each median into lengths with a 2-to-1 ratio. Here's what it looks like when I set up my coordinate proof. One of the vertices of the triangle will be on the x-axis, another will be the origin, and the third in quadrant 1. So I'm calling this x value 2a, this y value 0. The x and y values for this will be 2b and 2c, and of course the origin is 0, 0. Now the reason I chose to double these variables is that it makes the coordinates of the midpoint nice to work with. We don't have any fractions. Now let's look again at the two medians. I have a purple median right here from the origin to the opposite midpoint, and I have this tan colored median from this vertex to the opposite midpoint. The one I'm really interested in working with is this purple one, but the conclusions will apply to any of the medians of this triangle. Alright, so back to the two medians. In order first to get the coordinates of the centroid, I'm going to eventually get over here, get an equation for each of the medians, and then solve using algebra. But before that, let's calculate the slope. First of the purple median. C minus 0 over a plus b minus 0. C over a plus b. So what I have now is the slope of this purple median. It is c over a plus b. And now I'll do it for the tan colored median. And this is our slope for the tan. Help me remember these two slopes when I plug them into our linear equations on the next slide. Alright, this will be the purple median, and I'm using the point of the origin as my x1 and y1 values. So what I get is y minus 0 equals, and our slope was c over a plus b times x minus 0. And this simplifies to y equals c over a plus b x. For the other median, which was tan colored, I'm going to use the point on the x-axis for my x1, y1, and the slope which we already solved for. So let's sub in c over b minus 2a for the slope, and x minus 2a. That was the x value of the point on the x-axis. And when I simplify, I get y equals, now the solution. Remember that what we want now is to find the intersection point of the two medians algebraically. So since each of these equals y, what I'm going to do is substitute. Alright, there's step 1. Now I'm going to subtract this from both sides, which I now have here. Now I'll factor an x out of this. Now I will combine these two fractions into a single fraction. Feel free to pause the video and double check the algebra. So my new simplified equation reads like this. In order to isolate x, I want to multiply both sides by the reciprocal of this. I will also factor out a c from this numerator, which is becoming the denominator in this step. And now what we can do is some simplification. In this monomial I have a factor c, and I have a factor c which I can reduce. b minus 2a is both in the denominator and the numerator. And let's simplify this expression right here. b minus 2a minus b minus a. This becomes negative 3a. So these b's, actually b minus b gives me a 0. Let's take a step to simplify what we have here. I now have negative 2a times a plus b over negative 3a. And the negative over negative gives me a positive, and a's reduce, and so I get x equals 2/3 times a plus b. If you've lost track of what we're doing, we're finding the x value of the centroid. So now that I have it, 2/3 of a plus b, I can plug this into either equation, either this one or this one, to solve for y. And I think what I'll do is I'll plug it into this equation, which gives me y equals c over a plus b times x. And I just found out that x is 2/3 times a plus b. I'm going to put that over 1 so that we can see these a plus b's will reduce, and my y value is 2/3 c. So this is my x value for the centroid, and this is my y value for the centroid. Now let's take a look at the original picture again, and let's put our 2/3 of a plus b, and what was the other one? Oh yeah, 2/3 of c. Ignore that. Those are my coordinates for the centroid. Alright, here's where the fun really starts. Distance formulas. So remember, now what I'm doing is I'm getting this distance of the purple one, I'm getting this distance of one piece of the median, which I'm calling the green segment, and then I'm going to get the other piece right here, which I'm calling the red segments, and I have copies of them later, and we'll get to our conclusions in a moment. Let's first prove with some distance formula. So the distance of the entire median is, now for the green piece, and this is the green distance. Notice that it's almost exactly the same as the entire median, except for it's being multiplied by 2/3. Now for the red piece, I end up with 1/9 a plus b squared minus 1/9 c squared. This is the distance of the red piece of the median. Let's factor this 1/9 out of both. Now I have 1/9 of a plus b squared plus c squared. And we had a plus b squared plus c squared in each, so I end up with the square root of 1/9 times a squared plus 2ab plus b squared plus c squared. 1/9 is also a perfect square. If I take the square root of it, I get 1/3. This is the distance of the red segment, the green one, and the entire one. Now let's make some ratios. Let's compare purple to green, purple to red, green to red. So here again, let me demonstrate. I've just copied this purple distance, which is the entire median. I've copied this green segment, which is one part of the purple, and I've also copied this red piece right here, and the segment addition postulate tells me that green plus red equals purple. What we're trying to prove, though, is that this ratio is 2 to 1 for green to red, so let's start with that. I'm going to take the actual distances, and remember a ratio is division, so I went green divided by red in a fraction. So this is my green to red ratio. And let's take what we got for our distance from the green. We got divided by what we got for the red distance. Now if you haven't noticed, these radical expressions are exactly the same in numerator and denominator, so those reduce to 1. And basically all I need to do now is do 2/3 divided by 1/3. 2 to 1 ratio. So there is our proof that the green, this green piece, is exactly 2 times the distance of the red piece. This is true for any centroid, as it cuts any median of any triangle into 2 pieces. For fun, let's just get a couple more ratios here. Let's try to compare green to purple. So what's the relationship between this distance and this distance? So this is my green to purple, and purple again is representing the entire median. Again, these radical expressions reduce to 1, and I'm left with 2/3 divided by 1, which is just 2/3, and there is our ratio. The green, this piece right here, is 2/3 of the purple. Our last comparison, we're comparing the red distance to the purple distance. So our red to purple ratio, the whole distance, which is square root of a squared plus 2ab plus b squared plus c squared. These reduce, and we get 1/3 divided by 1, which is 1/3, 1 to 3. So there we have our 3 ratios. Thanks for watching, and keep practicing.